sentito? Sì? Okay. Okay, we can start again. And now we are about to talk about noise screens. Um, this drawing is showing you a source, okay, this point, and a receiver, and a rectangular screen between the source and the receiver. The sound coming from the source still arrived to the receiver through refraction over three edges of the screen: the upper screen, the upper edge, the left edge, and the right edge. It can also arrive from reflections and through the screen if the material employed to building the screen has not enough sound attenuation. If, for example, is made by wood, which is not a strong insulator, the sound will pass through. Or if there are holes in the screen, it can happen that the sound will pass through. And we define the screen attenuation, delta L, also called insertion loss, as the difference between the sound level at the receiver before the installation and after the installation of the screen. How we can compute this attenuation or insertion loss? Thanks to the Maekawa formula. That is this one. The first one is for a point source, okay? The second one is for linear source. This formula gives you the attenuation as a function of the Fresnel number. What is the Fresnel number? Is the ratio between 2 times this delta and lambda. Delta is the difference, the path difference between the direct path and the reflected path. And lambda is the wavelength. Okay. In the next slide, we can see a drawing, then make it maybe more clear. And this delta is the difference the difference between the sum of A and B and minus this D, that is the length of the direct path. Okay. Okay. No. Of course, the diffracted path is longer than the direct one. And to compute the Fresnel number, as I said, you have to divide this difference by the lambda. But this is equal to multiply twice the path difference. Where is the formula? Okay, in this corner, we can see that is equals to multiply 2 times the delta divided by lambda, but it is equal to multiply 2 times the frequency times the delta and divide it by c, that is the speed of sound. At this point, you can use this chart, and you can enter the Fresnel number and you can simply obtain the attenuation in decibel. As you can see, when the source is a point, the attenuation is bigger than for a line source. So the same screens will be more effective for a point source than for a line source. Shielding a line source is more difficult than shielding a point source. The noise overload propagates more heavily both with and without screens. This kind of source has the capability of bringing the sound behind the obstacle, while a point source is more easily controlled. First of all, its sound level naturally extinguishes with the distance more rapidly than a line source, and then the obstacles are more effective attenuating his level. Okay? So, what happens if the screen is not large enough? Okay, let's come back to the initial slide. Okay. What happens is that we have to consider lateral path. Those lateral paths are negligible as much as they are longer than the other path. Okay. If the screen is longer than 5 times the effective height, the side path can be neglected. And you can simply use the formula we have seen before that give you directly the attenuation of your screen. If instead you need to consider these two side paths, you have to compute the Fresnel number N1 and N2, okay, of the side path, and then you can compute the total attenuation of the screen as the attenuation obtained considering only the upper side, the one we considered before, minus this quantity. Okay, this. Oh, okay. And this will reduce the final attenuation. So when you design a noise screen, try to make it as long as possible, because the final attenuation will be much lower than the Maekawa prediction. Okay. Now let's talk about frequency. The Maekawa formula contains frequency, as we seen before. Okay. And so the attenuation will increase with frequency. If your noise source calls at the receiver a given noise spectrum when no barrier was installed, when you install the barrier, it will reduce a lot the high frequency sound and much less the low frequency sound. This means that it will change the spectrum of the source. So we can say that the noise screen is also a filter that attenuates more the high frequency and less the low frequency. This means that you cannot compute with this simple formula directly the total attenuation of a barrier, a single number that is telling you how much decibel the barrier is taking away, because it depends on the spectrum. So we have to repeat this computation at several frequencies. So, to compute the final level on a given sound, you have to apply the noise attenuation of the barrier in each band. For example, octave bands. And then you sum the band levels together. If you don't know the source spectrum frequency by frequency, but only its total level, you cannot compute the total attenuation. Okay? And it's is more or less all. Okay.